rotation of the Earth, it's got to be the entire face of the Earth rotates around one time. It takes a long time for it to do that. It takes a whole day. So it's 86,400 seconds under 2.5. Gives you 7.3 times 10 to the negative fifth. What's the unit on that? Radians per second.
Right.
Okay. So that's the first part. The second part is to take this and convert it. So this was a different value.
I think we just rounded up a little bit.
Yeah, but you got 7. They got 7.3, and you got 2.7.
No, that's number 2.
It's like
7.27.
Where am I looking?
Like it's number 2,
It's number
7.27.
Okay, erase
Oh, I get it. Alright, 7.27 times 10 to the negative fifth. Okay, times this is the radius, because v equals what you are, and that gives us the current speed that we're all moving at right now, 462.8 meters per second. That's how fast we're rotating. So even though we're standing still right now, that's our linear speed because we're standing on the face of the Earth.
Traveled 462 miles.
So in about 2 seconds, we've traveled a kilometer relative to our original position.
Whoa. That's
Ready?
amazing.
Ready? Hang on. 1, 2. There's a kilometer. There's a second. Okay. So we're moving really, really fast. Okay. Very good. Now, when things are rotating, because of Newton's first law, what do they want to do? Well, so suppose I start spinning this cup like this. Okay, it's got velocity, but say I let go. How's its motion going to relate to how it's moving if I let go? It's going to be tangential. Right? So it's going to go off in a straight line. So we're spinning right now on the face of the Earth. The force of gravity, and what's it do?
It holds us down.
It holds us into the Earth, which though means though, if we spin fast enough, the Earth started spinning faster because of some weird catastrophe. Who knows what would cause that? But if the Earth for some reason started spinning faster, eventually what would happen?
We get thrown off.
We fly off, right? But
That'd be like
before
the
that, the
scariest thing
atmosphere
ever.
would get sucked off, and we'd suffocate, and then we'd fly off.
That'd be crazy. We
It'd
just
be like, oh yeah, where's the sky going? The sky wouldn't be falling, the sky would be leaving. It'd be just like lifting off.
That'd be actually pretty
Terrible. So, but we'd probably all pass out before we get launched into space.
What if you were like a
We'd be
like a-
flying,
like a-
kind of.
What if you were like an astronaut training and you were like
So that's what question number 3 is asking: at which velocity would this occur? And what's interesting is if you look at this, we can look at this 2 ways. So if we set Fv equal to the centrifugal force, that maximum, we can find that maximum velocity. And so if we use the universal gravitation equation, mass 1 is just the mass of whatever's on the Earth. Mass 2 is the Earth. R squared is the radius of the Earth. This R is the radius of the Earth. And that's the velocity we're looking for. So when we solve for that v, we end up getting the square root of g, mass of the Earth over the radius of the Earth. And that would mean that for us to fly off into space, the Earth would have to start spinning at 7,909 meters per second. How much faster is that than it's spinning now, roughly?
like 7?
Roughly 20 times faster. Right, we're going about 460. So just rounding, like 400-ish.
Oh, yeah.
This is like 8,000-ish. So it'd be 20 times faster. So using that same kind of reasoning, how long would a day be roughly at that speed?
A little over an hour.
It's about an hour, right? Just be over an hour, 1.4 hours. So you figured it out. Yeah. So a day would be 1.4 hours. That means you could watch the sun.
It'd be like a strobe light. Like, wah, wah, wah.
Yeah, it'd be great.
That would be great.
All right. Now, there's another way to solve this too. This relationship is the same as this relationship. This is the force of gravity that holds us on Earth.
Why would you ever say that?
No, I feel like you'd actually age slower though, because like you wouldn't get that, you
Less
wouldn't get the
sunburn.
same amount like relatively.
All right, so
You age based on what you
hey,
get.
come on back. Here's
Sorry.
the weight, but we can also calculate it like this. Square root of RG. We've seen this. Get the same answer.
It's like 5
Don't be so picky. we use 9.81, it would be the same. All right. So, any questions about 3? Yes.
I'm kind of confused. Read this equation. What mass?
I can't see that, so I
Okay,
don't know what
fine.
you're talking about.
Sorry. Just ignore that. What mass do you divide by when you're doing?
This one?
Like, do you divide by 100?
So the 100 doesn't matter.
Oh.
Because in this equation, it cancels out. That's M1. M2 is the Earth. Mass 1 would be the 100 over here. And over here, it's the same. This is the mass of the object. This is the mass of the object.
So everything is black at the same one.
Yeah. Because remember, all that it depends on is the radius of the thing. And G. This is just like when we did the vertical loop, keeping the water in the cup. It's the same thing.
So when you do that equation with the M1 and the M2, you're finding the minimum amount of force to like keep them there.
Finding the maximum.
Max.
This one?
Oh.
This would be the max. This gives you the max. So at this velocity, things would fly off. Just under it, things would still stay on. And as this velocity increases, what happens to us? We start to feel lighter and lighter and lighter. Yeah.
So if it was just below the velocity that would fling us off, would we feel like lighter then? Because we're
Yes.
like about to
And if you
get flung
jump
off.
if you jump really hard, you could probably take off.
Whoa.
See you guys.
But again, this is all made up. This is going to happen. This can't happen. It's just for fun. We're just having fun.
Like
Thinking about it. I think
just like a little bit. How we feel.
Alright, let's
You can actually run away from your bomb.
5 seconds. Alright, let's take a look at number 4.
Trampoline could be super dangerous.
Yeah, go ahead.
Jump on that thing. and
Folks,
fall.
I can't hear Elena's question.
When you get F equals F equals Y,
What?
why does F equal F?
Why does FG? No, this is just to find that maximum speed. It's the same thing we did when we did the covenant.
Oh, well.
Yeah. Yeah, go ahead.
The gravity is pulling us down to the middle, or is centrifugal force that is keeping us from spinning off. So therefore,
Couldn't have said it better myself. Anything else? Great, let's look at the next one. Number 4. This is the wrong thing. This can't be. Oh, here it is. Number 4, what's the force of the gravity of the sun on you? So how hard does the sun pull on just little old you? So who did this one? Okay, go ahead, show us what you did.
So what we did first is the distance to the center of the Earth and the center of the Sun, and subtracted the radius of the Earth from it, because there was just only the distance of the Earth.
Very good. So that's the radius between you and what?
Between you and the Sun,
Which part of the sun?
the center of the Sun.
Very good.
So that is 1.5 times 10 to the 11, so that goes to the bottom. We did the massive thing here, so it's 70.91 kilograms. Times the mass of the sun which was given to you. So you multiply this together, divide by that, multiply that, and we got 0.418 meters.
Yeah, sun, that's about right. So the sun pulls on you with about 0.14 newtons, which is imperceptible because we're on the surface of the Earth. The Earth's pulling so much harder. And that would only be if you were on a piece of the Earth directly from the sun. We're usually center. Yeah. Questions? Yes.
If you did it, I mean, we set up a problem, but we added the Earth.
So no, this is the correct way to do this. You have to account for the difference from the Earth's radius.
Oh, no.
But you have to have your radius, so from the distance from the Earth to the sun plus the radius of the sun.
I'm sorry, we added the radius of the sun because we thought it was
0.412.
sun, not.
So if you add this
8.
and this, then you're good.
Oh,
That's what they did.
Oh yes.
okay, oh,
If you add those two numbers, then you've done it right.
okay.
That's what they did. They just did it a different way. They were using a number from a previous problem, I think. But yeah, that essentially is the same number. Okay?
Pardon me, interruption, but can the boys and girls track team please be released at this time? Thank you.
Alright, next one. We are now gravity, the sun, and the earth. Look at this. Number 5. Okay. That's right.
So E equals M1 times M2 over R squared, so V, mass of the earth, mass, mass of.
Go backwards. Mass, sun, mass, earth. There you go.
Mass of the earth over the, basically the radius of the sun and the earth and the, distance between the two added together, and the three zeros are 2 meters square and about 3.5 times 10 to the 27 meters.
Outstanding.
Wait, that's for which one? What's the?
5. Force of
that-
gravity of the sun.
It's on that 1, 2, 3, 4, 5. It's those numbers. No, not 1, 2,
It's not
Yep.
on then.
Should be huge.
4.
Alright, number 6.
Okay, so for number 6, we found W and R before plugging it into V equals WR. So to find W, we use 2 pi over this big number because this is how many seconds there are in a year. And so we got 1.99 times 10 to the -7
What's the unit on that?
rad per second.
Radians per second. Very good.
And then to find the radius, we added all the distances, although we weren't as exact as Jonathan. We just used 1.5 times 10 to the 11. And then we multiplied those to find V, which is 29,850 meters.
So that's the tangential speed of the Earth as it does what?
Orbits around the sun.
Orbits the sun. Excellent. So that's how fast we're all moving right now too, being attached to the Earth. So we're spinning fast and going fast. Very good. The second part of 6, let's all do this together. So, how are we going to figure out how much time it takes for the Earth to orbit? We already know the answer to it. What is it? 365 days. So, we know the velocity equals what over what? Distance over time. Now, we're assuming that the Earth's orbit is completely circular, which is not true. Well, we're just going to assume that it is to make it easier. So, our distance is what? 2 pi r, where r is the what? Distance between
The sun and the
the
earth.
sun and the earth, okay. And then our time is,
5 days. Well, we transfer into minutes.
oh wait a minute, we're solving for t. So it should actually be t equals
dv.
d times v, right?
Yeah.
No, d over v.
Yeah.
Right, so it's 2 pi r over the velocity, which we got there, 29,850. Okay. And what's our radius, friends? 2 pi times the radius. What is it? You got it in front of you?
Wait, where'd you get 29,000?
What is it?
Oh.
1.5 times 10 to the 11. Okay. Over this. Go ahead, everybody. That is the velocity we just found over there.
No, I put it above that. There's a line above, like, where you wrote out a distance, right?
Mistake.
Mr. Christie, does the Earth revolve in this? I mean, rotate in the same or opposite way in which it revolves?
Wait, is this the Earth?
If you don't know, it's
I'd have to look that up.
oh, okay. I'll just Google it.
What makes the Earth?
Did it work?
31 quick passes.
31.5.
It's pretty close. It's a little off just because 1.5 times 10 to the 11th is rounded.
So it's pretty close. It should be, we know it should be 315, 36, 000, right? What about that? What'd you get? 3-1?
We're like 400,000 off.
Could that be a quarter of a day or is that?
How long is it?
60.
What is
No.
its unit for?
Let me just give a round.
Seconds. Time, seconds.
Huh?
Yeah, it's 31.
Oh, man.
Follow me on Twitter.
No, bro, it's okay.